There we go.
Great. Thank you very much for that introduction. It's my pleasure to be here to talk to you today. Particularly, thank you for the invitation. My background, as Claire mentioned, is in AGN. I particularly think a lot about quasar broadline regions. But what I'd like to talk to you today about is this ongoing search for supermassive black hole binaries that I've been leading. So this is an observational search for these kinds of close gravitationally bound binaries like you see in this background image from a simulation at NASA Goddard. And like many efforts in astronomy, this has been a group effort. So you can see my collaborators are listed at the bottom. And I just wanted to highlight that we've had some really wonderful students working with us whose names are listed in orange, and I'll show you some of their work today as well. So the idea that that you should have supermassive black hole binaries really starts with galaxies. We see lots of different shapes and colors and sizes of galaxies. This is the Hubble Extreme Deep Field, which is what you see if you point the Hubble Space Telescope at an apparently blank patch of sky that has the angular size of a fraction of the full moon, and it's teeming with galaxies. And we think that most, if not all, reasonably massive galaxies host a supermassive black hole in their center. And the best evidence for this paradigm is in our own Milky Way. So this work has been very much in the news because it was the topic of the recent Nobel Prize in Physics. But over the last couple of decades, there's been this great effort to track the positions of stars in the center of the Milky Way. So you can see each of these little rainbow hotspots is a star in the Milky Way center. And over the course of 20 years or so, you can see that they all move around this position that's marked by this little white star. And this is the dynamical center of the Milky Way. And even just using the position of this S2 star, which has gone more than one time around its orbit, and using Newtonian gravity, this places the mass of the central object at about 4 million times the mass of the sun. And you can't explain that with all of the stars in this picture, particularly because you need that mass to be inside of the orbit, of course. And so really the best explanation for these changes in position is a central supermassive black hole. And even more recently, the gravity collaboration has done interferometry to really beat down on the confusion of sources in this central region. And they captured the sort of closest approach of this S02 star, which was missed the first time just because they didn't know when it would happen. And so now, you know, they've been able to measure the gravitational redshift and the precession of the perihelion. And so this is all, I think, really the best evidence that we have for this picture where galaxies, when they're, you know, reasonably massive, sort of normal galaxies, will host supermassive black holes in their center. Now, on top of this, we think that the way that cosmic structure and galaxies are built up over time is that you have this process of mergers and accretion, this hierarchical galaxy evolution picture. And it may be the case that really major mergers are relatively rare, although we certainly see examples of them, as you do here. But it seems then really an inevitable outcome of this kind of picture where you have you know, galaxies that undergo, you know, many mergers over their lifetime, and they all host supermassive black holes, that supermassive black hole binaries should be the inevitable outcome of this picture. But they've been observationally very elusive. And we're very motivated to find them for a number of reasons. Besides just the fact that if you could observe them, it would be a nice confirmation of this picture and our view of how this process works. They've also been invoked to explain a number of observational phenomenon. So stellar cusps in galaxies, for example, if you look at the distribution of stars in the centers of galaxies, you find that the distribution climbs as you go inward, and then instead of reaching a peak, there's like a flat-topped distribution of stars. And you could explain something like that if you had a binary in the center scattering stars out from small radii. Another phenomenon is X-shaped radio sources, which you can explain if your jet is processing around. And I think one motivation that's very exciting to me is that at their closest separations, these become bright, low-frequency gravitational wave sources. And so there's a lot of sort of leverage you can get with multi-messenger astrophysics. So we really would like to find supermassive black hole binaries for a number of reasons. I've been a little misleading, I think, to say that because galaxies merge, you should have gravitationally bound binaries. And there's a lot that happens sort of between those two stages, which is basically to say the physics of binary evolution, which is encoded in this little cartoon. So this is showing you the timescale that binaries would spend at different separations from sort of kiloparsec scale galaxy mergers on the right down to coalescence at the left. And the idea here is that you need some mechanism to remove angular momentum from the binary, and that will help it to spiral in, and the black holes will get closer together and it will move from right to left on this diagram. And the different mechanisms will describe how it moves on this diagram. So initially, you have this observationally normalized, kiloparsec separation dual systems that sync at first via dynamical friction and then by three-body scattering events with stars. And some of the early calculations for these scattering events found that you would run out of stars that could interact with your binary and take away angular momentum. And so the binary would stall at separations of about a parsec before it could get close enough that gravitational wave emission would be really efficient at evolving the binary to coalescence. So this is, if you've heard about it, it's called the last parsec problem. And it's not a problem anymore in the sense that there are many solutions to it in the literature. Do you have a question? No? Okay. So it's not a problem in the sense that we have solutions, quite a few, in fact. So one solution that's possible is that the initial calculations of these scattering interactions used symmetric gravitational potential. And if you use something that's maybe more realistic or is in some way is asymmetric, then you don't get this kind of stalling. And similarly, if you have any method for just replenishing the stars that have properties that let them interact with the binary, you can sort of get through these smaller separations. And another mechanism that's emerged is if the binary is embedded in a gaseous disk, torques from the circumbinary disk can help it to the black holes to move inwards and move across this sort of subparsec regime more efficiently. There's still a lot that's unknown. For example, which mechanism is at work? And I think as also more recent simulations of binary disks suggest that in fact, it may move the black holes outwards. So there's still a lot of work in this regime, I think, to be done. But one thing that is interesting is that if you could observe binaries with these properties at these sort of subparsec separations in this regime, it's possible that they spend more time here. So if you're looking for them, that would make them more numerous and easier to find. And if you could observe them, their distribution of properties would tell you something about the physics in this part of parameter space where we're not sure what's driving the evolution. The challenge is that at a pretty modest redshift, of 0.2. A parsec sub 10 is 0.3 milliarc seconds. So this is right at the limit of what you can do directly with radio interferometry. And as a result, we are relegated to using many different kinds of indirect detection methods to try to find these. So I want to just tell you a little bit about what those methods are. They tend to probe different phases of the binary evolution. So I'm showing you a cartoon now of the binary in the host galaxy evolving. I flipped it around. So now on the left, you have those dual kiloparsec separation systems, and to the right, you move towards coalescence. And at the widest separations, these dual kiloparsec separation AGN, we do observe. And the nomenclature here is that a dual AGN is like a pair that's not gravitationally bound yet, whereas a binary is gravitationally bound and will have to merge. So these dual AGN we do observe. They are still challenging to find observationally because in these cases, both black holes are usually accreting. And so you need evidence that you have two supermassive black holes accreting. And you can find this with, for example, Chandra by looking at the X-rays and finding X-rays in excess of what you can make with stellar processes. But these kiloparsec separations are at the limit of what Chandra can do. And so observationally, this is a challenging problem. Even though these are not gravitationally bound, they're very interesting to find because they are sort of unambiguous signposts that you've had a merger to bring these black holes together somehow. So Adi Ford was a graduate student at the University of Michigan, and she's now a postdoc at Stanford, and she did her thesis on this topic. She made a Bayesian tool to look at Chandra images and give you some statistical idea of how likely it is that you have two X-ray sources in a Chandra image. Whereas previously we've been doing this sort of as like a Rorschach test, like can I look and do I see two? And at the limit of Chandra's resolution, this has been actually a really effective method. At closer separations, you can do radio interferometry and try to find two flat spectrum radio cores that would indicate that you might have two accreting supermassive black holes. And this is really where the best example comes from. It's this CSO 0402. It's a 7 parsec separation system that's got these two flat spectrum radio cores. It was discovered in this Rodriguez paper. And Sarah Birks-Pallor did a search of first radio images to try to find as many of these as possible. It's difficult in the radio because you have this kind of pencil beam observing approach. And she recovered this 7 parsec separation system. And in this Bansal et al. Paper, you actually see the proper motion of the two radio sources. And so I think, you know, when I hear people talking in the field, there's these are hard to find, but I don't hear a lot of sort of noise about whether or not these are two supermassive black holes. I think the only question is, you know, at 7 parsec separation, that's sort of at the cusp of where things become gravitationally bound and you don't know the distribution of material and stars in the vicinity of the black holes. But if this is not a bound binary, it's probably quite close. So this is the one example that we have of, you know, what a supermassive black hole binary might be like. But if you want to go to closer separations, you are really pushing on radio interferometry, and we tend to use other methods. The method that I will go into great detail about in this talk is a radial velocity search. So I won't really say much more about that. But at closer separations, you have a number of approaches that are available to you. Mostly they revolve around the idea that when you have this circumbinary disk and you put a binary in it, you had to remove some of the gas that might have been there if you had just a single black hole. And so you see the signature of that in little notches taken out of the iron K alpha lines in X-rays around AGN and the spectral energy distribution. a third approach is to use changes in the brightness of quasars, periodic changes, either from Doppler boosting, which would give you a sinusoidal signal in the brightness, or for example, periodic accretion, which gives you more like a sawtooth signal. The challenge of these approaches is you have to somehow distinguish this from quasar variability, because quasars randomly get brighter and dimmer on their own. And the red noise, so they just get brighter and dimmer sort of slowly on average, can easily be confused with periodic signatures, especially if you don't see many cycles. There was a great sort of multi-messenger result from Alberto Sassana, which said that of the couple hundred or so binary candidates that are known from these photometric light curve approaches, they can't all be binaries, or you would have detected gravitational waves from them by now. And it kind of highlights one of the strengths of these approaches, which is that they're sensitive to sort of milliparsec separation systems, which are also gravitational wave emitters. And so you really can do multi-messenger astrophysics in this regime, but you're also very sort of subject to quasar variability. And I take that lesson very seriously, because it's, for me, also an issue with the method that I use. At the closest separations, you would have bright gravitational wave sources, and you could directly detect them with pulsar timing arrays or LISA, for example. Okay, so this radial velocity method has been used by a number of groups to try to look for supermassive black hole binaries. And the picture that you should have in your mind is completely analogous to what you would do with a stellar mass system. So this is just a heuristic example showing you several different phases of a stellar mass black hole and a massive star in a binary system. And if you can measure some spectroscopic feature from the star, say an absorption line, then you can trace its radial velocity over time, and you see this nice periodic signature that is indicative of binary motion. The reason I'm showing this is really to make 2 points. One is that these stellar mass systems, when you infer the periods and the masses from their radial velocity curves, you can see that this is the kind of system where you could go to the telescope, observe for a week, and really lay down the radial velocity curve. When you translate this to supermassive black holes, that's really not the case anymore. And so what that means is the signature that we're looking for is not a sinusoid at this point. What we would expect to see is a monotonic change, an increase or decrease in a radial velocity measurement, because the periods are expected to be quite long, decades to hundreds of years. And so you won't see many cycles of the radial velocity curve. You'll see just a little segment. And I'll talk later about what that really means for us and what we can do with this kind of information. But this is the test. And when you scale up to supermassive black holes, you get this picture. And this is the picture that we sort of love to hate in quasar astronomy, of quasar central engines. And what I actually want to do is talk about this in the context of what I actually look at, so that you can see how this test will work. So I'm going to save the cartoon and actually look at a quasar spectrum. So this is an optical spectrum of a quasar, and you can see a few different features. You can see the underlying sort of power law shape comes from the accretion disk, and the photons from this disk stream outward, and they encounter first gas in the broadline region. And this is really one of the limitations of this cartoon. I don't think of the broadline region in a quasar as being like levitating clouds above a disk. I think it's quite well shown that the gas in this region is not in discrete clouds, because you see these smooth line profiles, but it creates these broad emission lines in the spectrum. And they're Doppler broadened to thousands of kilometers per second. So this is gas that's right in the vicinity of the central supermassive black hole, and it's moving because of its gravitational influence. And we see that the gas is in a disky structure, and it's relatively dense to produce these lines. And so I think of the broadline region as maybe the outer extent of the accretion disk or a disk wind that's being lifted off of the disk. And the really important part for this search for binaries is that this gas is really in the vicinity of the black hole. On the other hand, on larger size scales, you have the narrow emission lines, which are also photoionized by the central source, but the gas is distributed more evenly in the host galaxy. And in fact, in the most luminous sources, they appear to actually saturate at very high narrow line luminosities. This gas is lower density because you're getting these forbidden transitions. And it seems to be sort of isotropically distributed. It is Doppler broadened to hundreds of kilometers per second. And so this gas is really in the gravitational potential of the galaxy, and not just the central supermassive black hole. So in a binary, this physical picture then changes a little bit. So this is what you should imagine. These on the left is a simulation of a supermassive black hole binary in a disk. But actually, the physics is the same as the simulation on the right, which is a simulation of planets migrating through disks around young stars. And the idea in either case is essentially the same. You can have gas that can stream across the gap, and it can fall onto one or both of the black holes. In this picture, the broadline region is right down in there around the supermassive black holes. So it's like a little mini disk inside of the circumbinary disk. And the narrow line region would be on very large size scales off of the slide in the host galaxy. And so you can imagine really two scenarios. And the first of these scenarios is that both black holes are active. And in that case, you might imagine you would see a source like this. So these are a class of quasars called double peaked emitters. And I'm showing you here their optical spectra for the Balmer lines. And you can see they have these whopping double peaked line profiles. And so the idea here was that those double peaked line profiles came from the broadline region, and they each came from one of the black holes. And the signature that you would expect is that the narrow lines set the rest frame of the galaxy, and then the broad lines would move back and forth as the black holes orbit around each other. And so this has been pretty well tested and rejected for a number of reasons in these sources. Both because we don't see that they do that. The peaks don't go like this when you monitor them for long time scales. It's actually the case that there's a very small part of parameter space where you would expect to see double peaked line profiles from a binary. And one thing that's very compelling to me is that their UV lines, where the physics is a bit different, are single peaked at the rest frame of the source, which is not what you would expect for bulk motion of an entire broadline region. So I think these have been ruled out, but we can learn some useful things. This is the radial velocity curve over about 20 years for one of the peaks in one of those line profiles. And you can see that it does drift in velocity space right up until it doesn't anymore. And so I'm very interested in quasar broadline regions and their variability to understand the kinds of things that can produce these signals without a binary. So keep this in mind, but there is still one case that is sort of interesting to look at and hasn't really been ruled out yet, which is the one black hole active case. So if most of the gas is falling onto one of those black holes, it's active, and the signature you might expect to see is something like this. So you have the broad line and the narrow lines in close proximity here with H beta and O3. And you might expect then that this bulk orbital motion would induce a velocity shift in the broad lines of some quasars. So this is the H beta spectrum. The dashed line is the rest frame that's set by the narrow O3 lines. You can see there's a narrow component to H beta, and you can see that the broad line has this large velocity shift U2, which is, if this is a binary, it's related to the actual orbital velocity by a phase angle and an inclination angle, which we don't know. we see shifts of order thousands of kilometers per second. And so this implies periods of order decades to thousands of years. So the periods are expected to be quite long. And so this is, again, why you expect the signature to be a bulk monotonic increase or decrease in that velocity offset. So the idea then going forward is that we take quasars with single peaked velocity offset broadlines and test the idea that that's the active member of a binary. So we went through Sloan, it was DR7, which is about 15 or 16,000 quasars with redshifts of order tenths, which is what you need to get that H beta region in your spectrum. And of those, 88 have these single peaked velocity offset broadlines. And this histogram is showing the distribution of those offsets. As I said, it's of order thousands kilometers per second. The dip in the middle of this distribution is not real. It is a symptom of our selection method, which included some visual inspection. And so this is essentially the part of parameter space that's occupied by regular quasars, which don't have offset broadlines. And so there are a number of other groups in the literature who have thought about those in the same context. So that's not really a missing part of parameter space. It's just not part of this particular program. And so we have these 88 binary candidates that were selected in this way. And right off the bat, just from their Sloan spectra, there are a couple of lessons to learn. So these are two examples of binary candidates, and I'm showing you their magnesium-2, their H beta, and their H alpha emission lines. And one thing that you could have noticed from the previous slide is that we see both red shifts and blue shifts. And this is important because quasars are known for having outflows that produce blue shifts in their broad emission lines. And so the fact that we see both red shifts and blue shifts gives us at least a little bit of confidence that we haven't just selected a big sample of outflowing quasar systems. Another thing you can notice is that when you see more than one emission line, they're all shifted in the same way. And that would be consistent with this bulk motion of the whole broadline region. Okay, so from here, then the name of the game is to do spectroscopic monitoring. And what's important at this point is that because the periods are expected to be long, you don't want to go out and observe very frequently. So this observing program has been pretty successful in the sense that we have managed to build up a number of observations per object, which is the distribution on the left, probing up to rest frames of order a decade in the rest frame of the quasars. And this long time scale is important because the periods are expected to be so long. So we're starting to probe some fraction of what you would expect the period to be for these kinds of systems. And so I've built the radial velocity curves, and these are the ones that fit on a slide. We have quite a few more, but these sort of show the general trends that we see. You see some examples like this one on the bottom left, where you measure the radial, the offset of that emission line, and it doesn't really change over time. And that would be consistent with a binary that just had a very long period. There are a couple of cases like this 094603 where we just clearly haven't sampled the radial velocity curve very well. And then there are these three examples, which are the best candidates for subparsec separation binaries, in the sense that we've been monitoring them for some appreciable fraction of what we think the period for these kinds of systems could be. And they're showing the monotonic change in the radial velocity that you would expect on those timescales for a binary. So they're consistent with that, that binary hypothesis. So would be something like this bottom left one. It's just, I think, a little less compelling or a little less interesting. Okay, clearly, the challenge of this approach is that when you don't see many cycles of the radial velocity curve and you don't see many cycles of the sinusoid, you can't really claim an unambiguous detection of a binary. But this radial velocity method is powerful in the sense that even without that, you can sort of get some leverage on the nature of the candidates. So what I want to tell you about now is the ways that we can try to learn things about the binary properties and place limits on what the binary properties can be if these are real. So here is a radial velocity curve for one of the candidates. And I could fit it with a sinusoid, and I should certainly not do that because I have like the same number of free parameters as I have data points. But what you can do instead is ask what the limit is on the period that this could have. If you assume that the period is not much shorter than your observations, which certainly can't be true because such a system would be too close to have a broadline region without destroying it. So if you assume that the period is not shorter than the observations, then by having this duration of observations, I've placed a limit on the curvature that the sinusoid can have. And so effectively you get a limit on what the period can be. And so at some statistical confidence, say 99%, the minimum period that this binary can have is a few hundred years. And assuming circular orbits, assuming the velocity offset that we observe for any geometry, the geometry of the orbit is unknown, for any mass ratio, which is also not completely known, the minimum period translates directly into a minimum mass. And if the mass that we calculate this way is bigger than any supermassive black hole that we've observed, then in order to have this binary hypothesis work out, you need a mass bigger than anything we've ever seen, which I think is sort of an unphysical situation to be in. And you have to revisit this idea that, okay, maybe these are not the binaries I was looking for. So this test has been really effective for the double peaked emitters to rule out their binary nature. I've done the exercise of calculating these mass limits for the single peaked binary candidates, and we get mass limits like 10 to the 8 solar masses. So for a total mass in a supermassive black hole binary, that's no problem. So these limits are essentially not restrictive yet, and they don't yet give us any insight into the nature of the candidates. So what is needed at this point is a longer time baseline, for one thing. So we've got maybe 5 years to 10 years, and some of the examples where this test is effective is 10 plus years. But another thing that's really important right now is radial velocity jitter, because it essentially serves to inflate the error bars that we have in a way we haven't characterized. And so this is my sort of main interest right now, is radial velocity jitter. What is jitter? It's random fluctuations in the velocity offset of the broadlines from time-dependent processes that happen around normal quasars. So it's like noise in a photometric light curve. And it can have different physical sources, and we know of some. So this is an example from a quasar reverberation mapping campaign. Reverberation mapping looks for the change in brightness of the central source, and then a light travel time later, the change in brightness is reflected in the quasar emission lines that are photoionized. So this top panel is showing you the change in the H beta flux over time, and the bottom panel is showing you how those emission lines, the H beta line, moves back and forth in velocity space to the tune of order 100 kilometers per second. And this is from a regular quasar. And so in this picture, you can see that this jitter, this velocity shift, is clearly related to the change in the flux. And what's happening here is that when the continuum goes up or down, the line responds to it, but it does it asymmetrically. And so one side will respond and then the other, and you get sort of little jitters in the velocity centroid of the line because of this asymmetric reverberation. And this happens then on timescales related to the reverberation process, which is weeks to months. So there are some sources of jitter that are known. What's not known is what happens on long time scales. And there's been very little work on this. And the Sloan Digital Sky Survey, the current iteration, Sloan 5, will be very good for this. On longer time scales, you open yourself up to different physical processes in a quasar broadline region. The dynamical time scale is of order a few years in a quasar broadline region. So you can have this kind of jitter and variability in the emission lines that comes from dynamical changes that we just haven't really studied well. So I think one of the biggest things right now for this search is that we need to sort of nail down what regular quasar variability looks like on these timescales, and to incorporate that into the analysis, because it'll basically tighten up the constraints on the mass. And there's another clue here that might help us to understand what's causing this line jitter, which is kind of an important one. So when we picked out this sample of binary candidates, what we find is that their line profiles are skewed in the direction that they're shifted. And this is important because it's a property of the sample. And so if we want to explain it, we need to know why this happens. And it's also the case that the line profiles are extremely variable. And to date, we have just avoided this issue by not measuring the radial velocity curves when the shape of the line profile changes. So there's a subset of the sample where we can't measure the radial velocity curves because of this. But this is something that we really should try to tie into the jitter measurements, because you can imagine with this asymmetric evaporation, the line profile shape would change. So there's sort of a missing axis of profile variability that we haven't dealt with yet. And then also this behavior that the lines are skewed in the direction they're shifted, which we can use for a couple of other tests. So I have a few minutes more, and I just want to go through a couple of other things that we're doing to try to constrain the nature of the candidates, because the test is quite difficult. It's very important to do many independent tests of the nature of the candidates. And by doing this, you can start to build up a picture of what their nature might be. Every test that you think of is an opportunity for an interloper to sort of show its true colors. And if you can make these tests sort of get at independent properties of the system, you have sort of more opportunity to gain confidence or to rule them out. So we have many observational tests that are going on. I'm happy to talk about these if anyone is interested. But I want to talk about a suite of theoretical tests that we're doing in addition, because I think they provide a couple of interesting ways about thinking about these systems. So the first thing is a project by an undergrad at Penn State. Her name's Alex. And she has been playing devil's advocate and doing the sort of alternative thing of asking whether we can explain what we're seeing with a single black hole. Do you really even need to invoke a binary? So this is a model of a quasar broadline region disk. You've got this sort of axisymmetric or asymmetric enhancement. Think about like a spiral arm in a disk. And as this processes around, it can make a peak in the emission line profile. You can see she's got this stack of profiles here, and the peak will drift in velocity space. And you might have, for a dynamical time that's some number of years, these sort of drifts in velocity space could persist for a while, certainly the duration of our observing campaigns. And so essentially we want to think about, could we be looking at something like this instead? And one question you have to answer is, does this model explain the shapes of the line profiles that we see? And the answer is sometimes. On the top panel here, you have two examples of binary candidates. These are the H beta spectra, and they've had everything subtracted except for the broad line. So the narrow lines are subtracted and the continuum is subtracted. And she's added some noise to her disk models on the bottom, and you can see that they do indeed produce some of the kinds of profile shapes that we see. There are some of the profiles that are quite a challenge to produce with this method. You can also do the exercise of assigning some timescale to that feature and processing it around, and measuring the radial velocity and seeing what you get. And indeed, you can get an answer that looks very similar to what we are seeing, even though this is not a binary. But there are some challenges for these models. One, I mentioned this observed correlation where the candidates' lines are skewed in the direction they're shifted. And for these models, you do see that, but sort of misleadingly, the axis ranges on these plots are quite different. So sort of the bulk properties are hard to recreate with just this model alone. And there's another sort of observational hiccup, I guess you could say. This model has been used to explain these double peaked emitters historically. They are well explained just by emission from a single disk that you can see in some fraction of quasars. So these are the broad lines of these double peaked emitters, which are typically associated with this model. And you can see as you go from left to right, they're not the same source, but what you're seeing is that in some sources, sometimes one of the shoulders of the line profile is very suppressed. And when that happens, what you get is a line profile that is asymmetric, single peaked, and offset in velocity, which is basically what we're seeing in the binary candidates. And so the idea is, maybe this model can describe them, and maybe they're just these double peaked emitters. But the UV lines then are sort of very enlightening to observe. So these are double peaked emission lines in these DPEs. And you can see that when you observe Lyman alpha in these systems, it's single peaked at the rest frame of the source. And I think that this is an optical depth effect. But you can imagine then that if these binary candidates are actually just sort of cases where you have one shoulder that's been squashed down, that their UV lines would be very interesting to observe, because in a binary, you would expect the UV lines to also be offset from this bulk motion, whereas with a single disk, that may not be the case. So this is the project that I'm working on right now. We have UV spectra for some of the candidates, and you can see that at least in some cases, we do see that the Lyman alpha and carbon-4 lines share the offset of the optical lines. Okay, I have a couple more minutes. And I just want to finish up by telling you about our efforts to do sort of the other side of things, which is to model the binary as a binary. And this work was led by Kai Nguyen, who was a graduate student at Georgia Tech. And he did the exercise of putting together a model of a binary. So you have two circumbinary, two mini disks and a circumbinary disk. And he calculated emission line profiles from these disks. He gave them a disk wind. And he makes basically a big library of what you might expect the H beta spectra to look like from these systems for lots of different properties of the binary, inclinations of the different disks, separations, mass ratios, and so on. So these plots are showing you the asymmetry versus the shift. So this is basically this plot of lines being skewed in the direction they're shifted. In the middle panel, you have the observed candidates. So you can see this sort of trend. In the left panel, you have the part of parameter space that's occupied by his models. And in the right, you have a regular sort of control sample of regular AGN that I made, where we had multiple epochs of spectroscopy from Sloan. And you can see that for the most part, they don't have big offsets, by definition, but there is still some range in the asymmetry. So really the takeaway here is that these binary models do occupy some of the same parts of parameter space as the candidates in this sense. Then he did the exercise of taking the observed spectra and trying to match them to spectra in his library. And he used a principal component approach to do this. And in the top panel, you're seeing 4 different spectra observed it. So it's like a time series for this one candidate in blue. And you can't, they're hard to see because they're very similar to the blue line. There's a dotted green line and dashed red line. And these are the most similar and most dissimilar within some statistical confidence profiles in his library. And you know, this is he's done sort of well, I did the spectral decomposition. And so this is the very high signals noise sort of average of the broadline component. So you can imagine as soon as you add noise that it would sort of subsume these differences. So once you've matched these profiles, you can ask what the properties of the binary were that made such a profile. And you can map the profiles back to physical properties of the binary. So that's what he's done. And you can see here the mass ratio versus separation that is implied in this kind of analysis. And it's suggesting mass ratios that are sort of relatively high and separations. These are in sort of theorist units, but I usually think of the quasar broadline region, the outer extent of it as being like 10 to the 3, 10 to the 4 in these units. And so this is about basically consistent with the picture that I've been telling you about this whole time, which is that you have room to have a quasar broadline region in this binary. Okay, that's fine, but you could do the same thing, right? You could follow this same process for regular quasars. You could match their profiles to his library of profiles, even though you know they're not binaries, and you would get an answer. And so what is that answer? Well, it turns out when you use this regular quasar control sample, they've got similar luminosities, similar redshifts. Regular quasars, when you follow this approach, will give you similar mass ratios and separations. And so what that means is you cannot use this to find binaries based on their shapes of their line profiles, because you can't distinguish them from what you would obtain from a regular quasar that's not a binary. But if you had a binary that you somehow had some confidence in its nature from something else, you could use this method to try to learn something about its properties. All right, we are about out of time. I can just summarize to say we've been searching for these supermassive black hole binaries. The radial velocity method is sensitive to subparsec separation systems, so they're not yet bright gravitational wave sources, but they're the progenitors of those systems that you would see with like a pulsar timing array or LISA or something like that. And this approach has given us, you know, some really good candidates, but what we really need to try to get some leverage on their nature is a longer time baseline and what's effectively a control sample of, you know, trying to understand what regular quasar variability can produce on these timescales. And then we've been doing a lot of sort of independent tests of the nature of the candidates, both trying to model them as single black holes to ask whether we really need to invoke this kind of binary explanation, and also trying to see, you know, if these are binaries, what can we learn from them and what can we do? So this is really ongoing work, and I think for my part, will really benefit from upcoming time domain spectroscopic surveys to try to nail down what quasars can do on longer timescales and sort of complement to the kinds of reverberation mapping that's long been done. So thank you, and I'll take any questions.
Excellent, thank you, Jessie. That was really interesting. I particularly like the anatomy of the system. This isn't my field, so I was like, I get that. Great.